Well, hello everyone. I hope everyone's doing well. I know I'm late as always, but we're here. I'm not gonna lie, I've been drinking a little bit too much caffeine. Whoa, my whole screen just kind of. I think we're okay. Okay. Anyway, not gonna lie, my sleep schedule. Well, I don't want to say my sleep schedule, but definitely drinking too much caffeine before I go to bed. That's why I'm kind of always slow in the mornings. I need to do better at going to bed on time and stuff like that. But anyway, what we're doing today, my name is Tyler Lamont. I'm studying for the CCNA. We are on day 16 of Jeremy's Tech Lab. If you have not subscribed to Jeremy's Tech Lab, you definitely should. It's really, really good. I am just a guy who likes tech. I work at a help desk IT, and I'm trying to just basically just learn as much as I possibly can. So we are going to rewatch part one, just because last stream it was very laggy, things are cutting in and out and stuff, whatever. So I just want to go through that really quickly, and then we will watch day 17, which is the day that we are actually on. And then we did not get to the packet tracer of day 16. If there is still time and I'm still feeling good, then we will do this guy over here that you see that's directly above me. Those are practice questions that I had AI created me a worksheet, so that way we can get better at subnetting and like questions about we need 500 subnets, at least 100 networks, things like that. So that's what we're doing today. Yeah, so let's go ahead and let's get into it. It should be pretty easy.
If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment and share the video to help spread this free series of videos. Thanks for your help.
All right.
So today's topic is another big one. Today's topic is VLANs. VLAN stands for Virtual LAN, Virtual Local Area Network. It's very important that you understand VLANs well for your CCNA exam, and certainly when working as a network engineer. So feel free to ask any questions if you don't understand. Here are the
Last time we also went down a really big rabbit hole.
First, what is a LAN? We know it stands for Local Area Network, but I'll give you a more specific definition. To help understand LANs and VLANs, we will also look at broadcast domains. After looking at LANs and broadcast domains, I will introduce you to VLANs, virtual LANs. I will teach you the basics of VLANs and their purpose. Finally, we will look at the basics of VLAN configuration on Cisco switches. By the way, this won't be the only video on VLANs. The next video, day 17, will also be on VLANs, so this video will just cover the basics. Let's get started. So, what is a LAN? In a previous video, I said that a LAN is a group of devices, PCs, servers, routers, switches, etc., in a single location, for example, a home or office. Let's take a look at a more specific definition. A LAN is a single broadcast domain. A broadcast domain is the group of devices which will receive a broadcast frame, that is, a frame with a destination MAC of all Fs, sent by any one of the members.
Okay, that makes sense.
Let's take a look at a diagram. So, take a look at this network here. How many broadcast domains do you think there are? Remember, a broadcast domain includes all devices that will receive a broadcast frame. So let's say PC1 sends a broadcast frame. And remember that a broadcast frame is a frame
only
with a
the router and
PC2
is going to get it.
Which devices will receive the frame? Well, this PC1 sends the frame out towards switch 1. And what does a switch do with a broadcast frame? It floods it out all interfaces, except the one it was received on. So the frame is sent to PC2 and R1. What does a router do with a broadcast frame? It doesn't forward it. It will receive the frame, but it won't send it to other networks. So that means this is one broadcast domain, including PC1, PC2, switch 1, and one of R1's interfaces. So that's one broadcast domain. How many are left? What if PC3 sends a broadcast frame? Which devices will receive it?
PC4, PC5, and router.
And flood it out of all interfaces to R1, PC4, and PC5. R1, however, will not forward the broadcast frame. So that's the broadcast domain. PC3, PC4, PC5, switch 2, and one of R1's interfaces. So far, we have found two broadcast domains. Now, how about if PC6 sends a broadcast frame? Which devices will receive it?
PC7, 8, and router 2.
When switch 3 receives it, it will flood the frame to PC7, PC8, and R2, and R2 will not forward the frame. So this is the broadcast domain, including PC6, 7, 8, switch 3, and one of R2's interfaces. So we found three broadcast domains so far. However, there is one more. What if R1 sends a broadcast frame out of its interface, which is connected to R2? It will be received only by R2. However, even though this is a connection,
that was definitely something that really kind of what I thought was very interesting, is that it's the interface. It's the interface that gets the IP address. So it's not the router itself. The router itself is the device that is managing all of the interfaces. So every interface is going to get an IP address. Every interface is going to have a broadcast. It's going to follow all the same protocols in terms of forwarding packets and stuff like that. Yeah, I thought that was very interesting because for me, I thought it was the device, not just the interface.
Only 2 devices, it is still technically a broadcast domain. So, do you understand what a broadcast domain is now?
Yeah.
A broadcast domain is the group of devices which will receive a broadcast frame with a destination MAC address of all Fs sent by any one of the members. In this network here, there are 4 broadcast domains, and therefore 4 LANs. Here is a small LAN of a company. Let's say there are 3 main departments in this office: engineering, sales, and human resources. Also, the company is using the 192.168.1.0/24 network for this LAN. However, this isn't necessarily the best setup. For both security and performance purposes, it will be best to split up these into separate subnets. For example, let's say a PC in the engineering department sends a broadcast message intended for other PCs in the engineering department. Since it's a broadcast message, the switch will flood it out of all interfaces.
Yeah, but it doesn't need to.
Not only will the PCs in the engineering department receive the broadcast, all PCs, as well as the router, will receive the broadcast. This is a problem for both security and network performance purposes.
Now, we could solve this problem with 2 things. He's about to go into VLANs, making a VLAN for each of these departments. But the other thing that you could do as well is that you could have a switch for each department. But then those switches go to this switch, or even switch out this switch with the router. But that's expensive.
When it comes to performance, lots of unnecessary broadcast traffic can reduce network performance. Whether it's a broadcast from one end host, or a switch that doesn't know how to reach the destination MAC address so it floods the frame, we should minimize unnecessary traffic in our network. As for security, even within the same office, you want to limit who has access to what. You can apply security policies on a router or firewall. Because this is one LAN, PCs can reach each other directly, without traffic passing through the router. So even if you configure security policies on the router, they won't have any effect. We should separate these hosts so we can apply security policies that determine who can access what in the network. So let's split up these departments into separate subnets. 192.168.1.0/26 for the engineering department, 192.168.1.64/26 for the HR department, and 192.168.1.128/26 for the sales department. However, there's one problem. The router is going to need an IP address in each subnet, so it will need one interface in each subnet. So let's replace this single connection between the switch and router with 3 separate connections, one in each subnet. Actually, there is a more efficient way of doing this. You don't actually have to use 3 separate interfaces, but don't worry about that for now.
Yeah, so what he did is he used 3 separate interfaces of this router, where the switch, this subnet, this department is going into the switch, and then it's being rerouted to this route, but they're all 3 different interfaces. But if you use VLANs, that's a virtual LAN. So what that would do is you would only have one interface. It would all be trunked into it.
I'll cover that in a future video. So you may think the problem is solved now. Let's say this PC in the engineering department has an IP address of 192.168.1.1, and this PC in the sales department has an IP address of 192.168.1.129.
They're in different subnets. They can't talk to each other.
If PC1 sends some data to PC2, PC1 will recognize that PC2 is in a different subnet than its own. So it will set the destination MAC address to its default gateway, R1.
Yes.
This is what the frame.
Yeah, because the subnet makes it so that way you can only talk to the grouping of that subnet. It's another level of just kind of security. I want to say that it's like super strong security, but it is an organizational and security measure. I would say that security by what is it, by default, or by man, I've been drawing a blank on words lately. Basically, it's just kind of happening, is what I'm trying to say. So, because it can't talk to this computer over here, so it needs to go to the router, and the router says, "Oh, I know where that's at," and then sends it to this subnet. This is why we went in that really deep rabbit hole that we went on last Wednesday, about IPv6, and because I had all these questions about security with IPv6. I'm sure we will get into IPv6 later in the course, but I just had a bunch of questions, and it just wasn't making a lot of sense.
Source IP of PC1, destination IP of PC2, source MAC of PC1, and destination MAC of R1. PC1 will forward the frame to the switch, which will send it to R1. which will then change the source MAC to its own MAC and the destination MAC to PC2's MAC. It will then forward the frame back to the switch, which will then forward it to the destination, PC2. Okay.
That's a good example of how the hops work too. This PC went here, and then it went here, and it changed its source MAC and its destination MAC, but its source IP and its destination IP stayed the same. Now my question is, do we know the IP address? Does the packet or the frame store the IP address of where it's of the hop and what hop it's going to? I don't know. It's a good question.
Okay, so instead of PC1 being able to send traffic directly to PC2, we forced it to send the traffic through R1 first, where we would have configured some security policies and such to control exactly what traffic is allowed to pass between these subnets. However, there is still a problem. Here's the problem. What if the frame is a broadcast or unknown unicast frame? The switch will flood the frame out of all interfaces. For example, here's a broadcast frame. The source IP is PC1's IP, and the destination IP is its subnet's broadcast address. So this is a broadcast frame intended to the engineering department. The source MAC is PC1's, and the destination is the broadcast MAC address of all Fs. Where is the problem? Well, remember that a switch is only aware up to layer 2. It looks at layer 2 information like source and destination MAC addresses only.
Yeah.
It doesn't care about layer 3, 4, etc. So, even though there are 3 separate subnets here, the switch doesn't know that. PC1 will send the frame to the switch, it will see the destination MAC address of all Fs, and then flood the frame. I'll say it again. This is bad in terms of both network performance and security. So I've shown you that although we separated the 3 departments into 3 subnets, meaning they are separated at layer 3,
you're basically just shooting out like,
in the same
hey,
domain,
who's there?
the same layer 2 network, or the same LAN. Now, one possible solution is to buy a separate switch for each department. However, that is not very flexible, and network equipment isn't cheap, so buying 1 or more switches for every single department could be too expensive, especially for a small enterprise. However, this is where VLANs come in. Although these PCs are all in the same LAN, local area network, we can use VLANs, or virtual local area networks, to separate them at layer 2. We'll assign the engineering department to VLAN 10, the HR department to VLAN 20, and the sales department to VLAN 30. How exactly do we assign these hosts to VLANs? We configure them on the switch. More specifically, on the switch interfaces. You configure the switch interface to be in a specific VLAN, and then the end host connected to that interface is part of that VLAN.
Okay.
The switch will consider each VLAN as a separate LAN and will not forward traffic between VLANs, including broadcast or unknown unicast traffic. So, if we have set up these VLANs, if PC1 sends this broadcast frame, after the frame arrives at the switch, it will be forwarded to all interfaces in the same VLAN. Because the broadcast arrived on an interface configured in VLAN 10, the switch will only forward the frame to other interfaces in VLAN 10. If PC1 wants to send the same unicast frame to PC2, it will function just like before. It sends it to the switch, which sends it to the router, which changes the source and destination MAC addresses, and sends it.
So are VLANs set up on switches? Are VLANs set up on switches only, or is it something that needs to be set up on all devices? See here. No, you do not have to configure VLANs on every single regular device, like your PC, smart TV, or gaming console, but you do need to configure them on infrastructure devices like switches, routers, and wireless access points. Here is exactly how it breaks down. Manage switches, where the heavy lifting happens. Switches are primarily devices responsible for managing VLANs. You configure individual physical ports on the switch to separate traffic. So it's more of a switch thing. Trunk ports, I knew that. Access ports and trunk ports. These connect to normal end user devices. The switch tags all incoming data from the port with the specific VLAN ID. The device is absolutely, the end device has absolutely no idea it is on a VLAN. So it is just strictly switch. And that makes sense because that's basically what he just said. So routers and firewalls required for communication. Because VLANs isolate networks, devices on VLAN 10 cannot talk to devices on VLAN 20. By default, if you want to communicate, you must configure those VLANs or VLAN aware routers to handle inter-VLAN routing. Access points required for Wi-Fi. That's getting a little bit beyond what we're doing here. Okay.
Sends it back to the switch, which sends it to the destination. Notice that the router is used to route between VLANs. The switch does not perform this inter-VLAN routing. It must send the traffic through the router. Notice that traffic arrives on a VLAN 10 interface and is forwarded out of a VLAN 10 interface. Also, traffic that arrives on the VLAN 30 interface is forwarded out of a VLAN 30 interface, both in the same VLAN. A switch will never forward traffic directly between two VLANs like this. Well, first of all, the two hosts are in separate subnets, so PC1 itself will send the traffic to its default gateway, R1. However, even if PC1 and PC2 were in the same subnet, the switch wouldn't forward the traffic from PC1 to PC2 because they are in separate VLANs. Just a bit of review. VLANs are configured on switches on a per interface basis. VLANs logically separate end hosts at layer 2. Although the hosts in the topology we looked at were physically connected to the same switch, and therefore in the same broadcast domain, we used VLANs to logically separate them and put them in separate broadcast domains. Switches do not forward traffic directly between hosts in different VLANs. As I showed you, the switch must forward the traffic to a router. Actually, there are a couple other methods of inter-VLAN routing.
Okay, so that means if we have a VLAN, like how I was just talking about with those three right there, the switch only knows, it's just like, oh, okay, that grouping, that VLAN is over here, but I can't do that. I have to send it to the router, and the router. It's kind of like how mail works. Like, I don't know if you know this, but in Houston, basically, there's like these little I don't know exactly how it's all divided up, but basically if I wanted to send mail, it's got to go to Houston first, and then Houston sorts it from there. It's very, very, very interesting. I am very
I will
thirsty.
cover them in a future video.
I don't want no stupid
Finally,
Pepsi.
let's take a look at basic VLAN configuration. I've added the interface numbers to the diagram. Interfaces in VLAN 10 are G10 through G13. Interfaces in VLAN 20 are G20 through G22. And interfaces in VLAN 30 are G30 through G33. Let's go into the CLI and put these interfaces into the proper VLANs. Before configuration, let's look at the VLANs that exist by default on a switch. In this output, you can see I use the command show VLAN brief. It displays the VLANs that exist on the switch and which interfaces are in each VLAN. Here you can see VLAN 1 with the name default. This is the VLAN that all interfaces are assigned to by default. So even if you don't configure any VLANs, all interfaces are in VLAN 1 by default. Under ports, you can see all of the interfaces on this device, from G00 to G33. Under it are 4 other VLANs, 1002 to 1005, used for FDDI and token ring. These are old technology.
We did some deep dive into this last stream. These are all legacy things for old routers and switches and stuff, so therefore we can't get rid of them.
Technologies that you don't need to know for the CCNA.
I wonder what the life expectancy is for that.
VLANs 1 and 1000 to 1005 exist by default and cannot be deleted. Remember that. This is how you assign interfaces to a VLAN. First, I use the interface range command to configure all of the VLAN 10 interfaces at once. Use the switch port mode access command to set the interface as an access port. What is an access port? An access port is a switch port which belongs to a single VLAN and usually connects to end hosts like PCs. That's why it's called an access port. It gives the end hosts access to the network. There is another important type of switch port called a trunk port. Switch ports which carry multiple VLANs are called trunk ports. I will cover trunk ports in depth in the next video, but for today's video, we'll focus only on access ports and take it step by step. A switch port connected to an end host should enter access mode by default. However, it's always a good idea to explicitly configure the setting and not rely on auto-negotiation of port type. Anyway, the last command after switch port mode access is switch port access VLAN 10. This is the command that actually assigns the VLAN to the port. Notice the message that appears after this command. Access VLAN does not exist. Creating VLAN 10. Because VLAN 10 didn't exist on the device yet, it was created automatically when we assigned the interface to VLAN 10. I'll show you how to manually create a VLAN in the next slide. Next, I again use the interface range command to configure all of the VLAN 20 interfaces at once. I use the same switch port mode access command, then switch port access VLAN 20 to assign the interfaces to VLAN 20. Finally, I did the same for VLAN 30, and once again, the VLAN was created automatically. So, I used the show VLAN brief command once again, and here you can see the 3 VLANs we created, and the ports we assigned to each VLAN. Notice the default names of each VLAN. Let's change those to make it more understandable. So I used the VLAN 10 command to enter configuration mode for VLAN 10.
Okay, that's
By the
super
way,
simple.
this is the command to create a VLAN also, but in this case, it was already automatically created when we assigned the interfaces. Next, I assign the name with this simple command, name engineering. Then I do the same for VLAN 20, HR, and VLAN 30, sales. Finally, I confirmed once more with show VLAN brief. Notice that the names have been changed to engineering, HR, and sales. Okay, so that's...
Do VLANs have to be in groupings of 10, or can they be anything? Do VLANs have to be in groupings of 10, like VLAN 10, VLAN 20, VLAN what was that? 30? Yeah, because that's what it says up here, right? Yeah. Or can I have I'm pretty sure I can have VLAN 2. No, VLANs do not have to be grouped in groupings 10. You can use any number from 1 to 4094 for your VLAN ID, including VLAN 2 or VLAN 7. Skipping by 10s is simply a popular industry best practice used by network administrators. It provides room for insert new networks later without breaking the organization. Oh, so it's for organizational purposes. Okay,
that's all for the configurations. If I use the command ping 255.255.255.255 on PC1, which sends a ping with the destination MAC address of all Fs, the broadcast MAC address, the broadcast will only reach hosts in VLAN 10. Likewise, if I use the same command on PC2, the broadcast will only reach PCs in VLAN 30. Okay, so before moving on to today's quiz, let's review what we covered. We talked about what a LAN is, and I defined it as a broadcast domain, the group of devices that will receive a broadcast frame sent by another member in the group. Then I talked about what a VLAN is. It's essentially a way to logically split up a layer 2 broadcast domain to make multiple separate broadcast domains. We also talked about the purpose of VLANs. The 2 big reasons are network performance and security. VLANs help to reduce unnecessary broadcast traffic, which helps prevent network congestion and therefore improve network performance. Limiting broadcast and unknown unicast traffic like this also improves network security, since these messages won't be received by devices outside of the VLAN. You should always make sure that network traffic isn't sent unnecessarily to other devices, as much as possible. Finally, we looked at how to configure VLANs on Cisco switches. Specifically, we configured access ports on a Cisco switch and assigned them to a specific VLAN. There is still plenty to cover about VLANs, but this should be a good foundation. In Day 17's video, we will cover more topics regarding VLANs. Okay, let's
quiz
go on
time.
to today's quiz. First up, question 1. How many broadcast domains are shown in this network diagram? Pause the video and count how many broadcast domains you see.
So we have 1, 2, 3, 4, 5, 6. Yeah, there's 6.
Note that no VLANs have been configured, so all hosts are in the same default VLAN, VLAN 1. Pause the video now.
Done did it.
Okay, let's check the answer. There are 6 broadcast domains in this network diagram.
Nailed it.
Basically, each router interface and everything connected to it are in one broadcast domain, since no VLANs have been configured. Let's go to question 2. How many broadcast domains are shown in this network diagram? Take note of the configured VLANs. Pause the video to think about your answer.
1, 2, 3, 4, 5. There's 5 of them.
Okay, let's check. There are 5 broadcast domains here, 1 for each of the configured VLANs, and the connection between the 2 routers is a broadcast domain as well. Let's go to question 3. What happens if you try to assign a switch interface to a VLAN that doesn't exist? A, the command will fail. B, the switch will create the VLAN. C, the interface will be disabled until you create the VLAN.
What happens if you try to assign a switch interface to a VLAN that doesn't exist? I think that it'll just create the VLAN, because didn't he say that it was the same command?
Or D, all VLANs exist by default. Pause the video to think about your answer. Okay, the answer is B, the switch will create the VLAN. As I showed earlier in this video, if you assign a switch interface to a VLAN that doesn't exist yet, the switch will create the VLAN automatically. Let's go to question 4. If PC3 sends a broadcast message, how many devices will receive it? Pause the video to think about your answer.
So your PC3, the only devices that will receive it will be the switch, this PC that's over here, and the router.
Okay, let's check the answer. The answer is 3. First of all, the switch will receive it. Then it will send it out of all interfaces in VLAN 20, so the router and the other PC in VLAN 20, making a total of 3 devices. If no VLANs were configured, all other PCs would receive it. But since we have configured VLANs, only these devices in the same VLAN will receive it. Let's go to the final question, question 5. You create VLANs 10, 20, and 30 on a Cisco switch. How many VLANs will be displayed in the output of the show VLAN brief command? A, 3, B, 5, C, 8, or D, 10?
No, it's going to be 1, the default, 10, 20, 30, so that's 4. And then I'm pretty sure that there was 4 legacy. I'm pretty sure it's 8.
Pause the video to think about your answer. The answer is C, 8. Let's check it out. As you can see, there are 8 total VLANs. VLANs 1 and 1002, 3, 4, and 5 exist by default and cannot be deleted.
Yep.
So if you create 3 additional VLANs, there will be a total of 8 VLANs on the switch. Okay, that's all for the quiz. There will be supplementary materials for this video to help you review and practice what you've learned. There will be a flashcard link in the video description, which you can use with the flashcard software package to help you review.
They're
There will
so
also be a
good,
packet tracer
but
practice
God, they're
lab,
boring.
which you can use to practice the configurations learned in this video.
We're going to do the packet tracer. Not right now. We're going to go directly to day 17 and listen to it. However, I am going to go grab some tea real quick. I'll be back in like literally 1 minute because I got to go heat it up. So here, listen to some music. There you go. Okay, we'll knock this down a little bit. All right, let's do it. Let's get to it. Let's knock it out.
Like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. In this video, we will continue with the topic of VLANs, Virtual Local Area Networks. In the last video, Day 16, we covered the absolute basics of VLANs, what a VLAN is, what their purpose is, and the most basic VLAN configurations. However, that's not really enough information. There is still more basic knowledge you need to be able to understand and use VLANs. That's what we'll cover in today's video. So let's take a look at what we'll cover exactly. This will be a fairly long video, I think, but let's take it step by step. First of all, what is a trunk port? I mentioned trunk ports briefly in the last video. Whereas an access port belongs to a single VLAN, trunk ports carry traffic from multiple VLANs on a single interface. Next, what is the purpose of trunk ports? How are they actually used? Next, I will talk about 802.1q encapsulation. This is an additional tag added to an Ethernet frame, which is used to identify which VLAN traffic belongs to on a trunk. Next, we'll go into trunk port configuration. It's not so complicated, you only need to learn a few more commands. Finally, we'll cover router on a stick. It's a bit of an odd name, but this is something you really need to know for your CCNA. It's a more efficient way of performing inter-VLAN routing, an alternative to using a separate router interface for every VLAN. So let's get started. For a quick review, here is the network topology used in the last video. There is a single switch and 3 VLANs. All of the switch interfaces are access ports, which belong to a single VLAN, either VLAN 10, VLAN 20, or VLAN 30. 3 interfaces are used to connect to the router, one for each VLAN. For this video, let's use a different network topology. Here's the network topology we'll start with for this lesson. This time there are 2 switches used. Note that VLAN 10, the VLAN for the engineering department, is split between the 2 switches. This is very common, as departments in a company aren't always split up exactly by location. You might have some engineers on one floor of the building, for example, and some on another floor. We are still using only access ports. There are 2 links between switch 1 and switch 2, one for VLAN 10 and one for VLAN 30.
Okay.
There must be a link in VLAN 10 between the 2 switches because VLAN 10 PCs are connected to both switch 1 and switch 2. And also because the PCs connected to switch 1 need to be able to reach R1 via switch 2. As for the link in VLAN 30, it is necessary because PCs in VLAN 30 also need to be able to reach R1 via switch 2. There is no link in VLAN 20 between switch 1 and switch 2. This is because there are no PCs in VLAN 20 connected to switch 1. PCs in VLAN 20 can still reach PCs connected to switch 1. R1 will perform the inter-VLAN routing. Let me demonstrate that inter-VLAN routing. Let's say this PC in VLAN 20 wants to send traffic to one of the VLAN 10 PCs connected to switch 1. It will send the frame with a destination MAC address of R1, its default gateway. R1 then forwards it back to switch 2. Note that this traffic arrived at switch 2 on the VLAN 10 interface. The traffic is now in VLAN 10, so it forwards it to switch 1 on the VLAN 10 connection between them. And then switch 1 forwards the traffic to the destination PC. So you can see that even though there isn't a VLAN 20 connection between switch 2 and switch 1, the PC in VLAN 20 can still send traffic to the PC in VLAN 10 because the router performs inter-VLAN routing. In a small network with few VLANs, it is possible to use a separate interface for each VLAN when connecting switches to switches and switches to routers. However, when the number of VLANs increases, this is not viable. It will result in wasted interfaces, and often, routers won't have enough interfaces for each VLAN. You can use trunk ports to carry traffic from multiple VLANs over a single interface. Once again, these are different than access ports, which belong to a single VLAN only. Let's take a quick look at how trunk ports work. So, now I've replaced those separate connections for each VLAN with a single connection between switch 1 and switch 2 and R1. However, to make it more clear, let's add those colors back. Okay, so now you can see which VLANs are allowed on each trunk. Remember, these are single physical connections, but traffic from multiple VLANs is allowed over each trunk. Let's say this PC in VLAN 10 wants to send some data to this other PC in VLAN 10.
Whew.
It sends the traffic to switch 2,
Almost spilt my
which
tea.
then sends it to switch 1.
Virtualization blows my mind. So, we have a LAN, which is just a cable, okay? Connects 2 computers together. But now we have a virtual LAN, which is a virtual cable that is connecting different groups together. And the reason we're calling it a virtual LAN is because you can segregate different groups of devices with just a wire, right? But now we're doing this virtually. But in order to do it virtually, we need to make sure that we're going to the right interfaces. So we need to then regroup them, but yet they stay separated. Does anybody else think that's kind of weird? Or interesting? No? Just me? Just me doing my thing? Okay, cool.
Now, here's a question. How does switch 1 know which VLAN the traffic belongs to? Both VLANs 10 and 30 are allowed on the interface the traffic was received on. But how does switch 1 know which VLAN it belongs to?
Trunk port.
The answer is VLAN tagging. Switches will tag all frames that they send over a trunk link. This allows the receiving switch to know which VLAN the frame belongs to. In fact, another name for a trunk port is a tagged port, and another name for an access port is an untagged port.
Oh, so a trunk port is a tagged port, an access port is an untagged port. That's very important.
Over access ports aren't tagged. They don't need to be tagged because the interface belongs to a single VLAN. If a frame arrives on a switch port in VLAN 10, the switch knows the frame is in VLAN 10. Let's talk about those VLAN tags. There are two main trunking protocols, ISL, inter-switch link, and IEEE 802.1q. Usually we call 802.1q .1q. ISL is an old Cisco proprietary protocol, created before the industry standard IEEE 802.1q. .1q is an industry standard protocol created by the IEEE, Institute of Electrical and Electronics Engineers. Remember the IEEE? How about IEEE 802.3? That's Ethernet, another industry standard protocol.
Yeah.
You will probably never use ISL in the real world.
And then 802.11, which is Wi-Fi.
Even modern Cisco equipment doesn't support it. For the CCNA, you only need to learn .1q. You should know what ISL is, but you don't have to study it like .1q. Okay, here's an old slide back from day 5 on Ethernet switching. Do you remember the fields of the Ethernet header and trailer?
Yeah, bro. This is another one that freaking blew my mind with how it works. The preamble, the SFD, destination source type, the actual packet, and then the FCS, frame check sequence, start frame delimiter. Man, it's like, this is all electricity. That also gets me too, is that this, man, it's just so interesting.
If you don't, I recommend going back to check out day 5's video. I won't waste time explaining it all again here. However, the reason I am showing this is because the .1q tag is actually inserted between two fields of the Ethernet header. So here's just the Ethernet header. .1q inserts a 4-byte, or 32-bit field between two fields of this Ethernet header. Let's take a look. As you can see here, the .1q tag is inserted between the source MAC address and the type or length fields of the Ethernet header. Let's go over some basics. As I just said, the 802.1q tag is inserted between the source and type/length fields of the Ethernet frame. The tag is 4 bytes, or 32 bits in length. The tag consists of
Also
two main
known as
fields.
a nibble.
Those are the Tag Protocol Identifier,
No,
TPID,
sorry, that's not a nibble.
and the Tag Control Information, TCI. The TCI itself consists of 3 subfields. Let's quickly take a look at each field of the .1q tag. Here's a diagram of the .1q tag format, thanks to Wikipedia. Notice that it can be divided into 2 halves, the TPID and TCI I mentioned before. Also, the TCI can be divided into 3 subfields, the PCP, DEI, and VID. Okay, first up, let's look at the TPID field. The field is 16 bits, or 2 bytes in length, taking up half of the 802.1q tag's length. The TPID is always set to a value of 0x8100. Remember, 0x just means hexadecimal, so the actual value in the field is just 8100, 4 hexadecimal digits. Each hexadecimal digit is 4 bits, so 4 times 4 is 16, the total length of the field. This value of 8100 indicates that the frame is .1q tagged. As I just showed you, the .1q tag comes after the source MAC field of the Ethernet frame. This is where the type field is usually located. When the switch sees this value of 8100 here, it knows it's a .1q tagged frame. Okay, that's all for the TPID field. Next up, let's look at the first field of the TCI, which is the PCP, or Priority Code Point. The field is 3 bits in length. It is used for Class of Service, COS, which prioritizes important traffic in congested networks. Don't worry about this field too much, just know the name and that it is used for COS. Next up is the DEI, Drop Eligible Indicator. This field is just a single bit in length. It is used to indicate frames that can be dropped if the network is congested, which makes sure more important network traffic gets through. Once again, you don't really need to worry about this field too much for your CCNA, just know the name and its basic purpose. Okay, finally is a very important field, the VID, or VLAN ID. It is 12 bits in length. It is the field that actually identifies the VLAN the frame belongs to, so you could say this is the most important field of the .1q tag. Because this field is 12 bits in length, that means there are 4,096 total VLANs, because 2 to the power of 12 equals 4,096.
Whoa, hold on. 12 bits in length identifies the VLAN and the frame belongs to. 12 bits in length equals 4,096 total VLANs, because 2 to the power of 12 range from 0 to 4,095. Oh, because we count 0. VLAN, so we're going to have VLAN 0? That's weird. Man, I'm losing my hair. Look at that. Look at that. That receding hairline. That's crazy.
However, the first and last VLANs, 0 and 4095, are reserved and can't be used. Therefore, the actual range of VLANs that can be used is 1 to 4094. By the way, Cisco's proprietary ISL, which is an alternative protocol for VLAN tagging over trunk connections, also uses a VLAN range of 1 to 4094. As I mentioned before, however, you don't really need to know ISL. It's almost being completely replaced by the industry standard .1Q. So, those are the fields of the .1Q tag. Take a look at this diagram. Do you remember the names of each section and their basic function?
Kind of.
If you want to read a little bit about .1Q, I recommend checking out the Wikipedia page for a solid overview of it. Okay, let me talk about the VLAN ranges a little bit more. The Wikipedia page for a solid overview.
I kind of want to do that. So, 802.1Q wiki. All right. Let's get a little bit more information here. Is he gonna read it to me?
IEEE 802.1Q, often referred to as .1Q, is the networking standard that supports virtual local area networking, VLANs, on an IEEE 802.3 Ethernet network. The standard defines a system of VLAN tagging for Ethernet frames and the accompanying procedures to be used by bridges and switches in handling such frames. The standard also contains provisions for a quality of service prioritization scheme commonly known as IEEE 802.1P and defines the generic attribute registration protocol. Portions of the network that are VLAN aware, that is IEEE 802.1Q conformant, can include VLAN tags. When a frame enters the VLAN aware portion of the network, a tag is added to represent the VLAN membership. Each frame must be distinguishable as being within exactly one VLAN. A frame in the VLAN aware portion of the network that does not contain a VLAN tag is assumed to be flowing on the native VLAN. The standard was developed by IEEE and 2.1, a working group of the IEEE 802 Standards Committee, and continues to be actively revised with notable amendments, including IEEE 802.180, IEEE 802.1AK, and IEEE 802.1, the 802.1Q to 2.1Q to 2.1D 2004 standard, which originally defined bridging
and the 802.1Q adds. Oh, and the span tree protocol, the spanning tree protocol. And then there it is. It's added right there. Wow. DEI. Drop eligible indicator. Double tagging. Oh, you can add double tags. Okay, very interesting. Very interesting indeed. Went a little bit too far. And let's go just a little bit more. All right, here we go. Let's continue.
Okay, let me talk about the VLAN ranges a little bit more. The range of VLANs, which as I mentioned is 1 to 4094, is divided into two sections. Normal VLANs, which are numbered from 1 to 1005, and extended VLANs, which are numbered from 1006 to 4094. Some older devices cannot use the extended VLAN range. However, it's safe to expect that modern switches will support the extended VLAN range. I work with...
I have a meeting. Oh my gosh. Oh my gosh. Okay.
Cisco switches
we're
a
not
lot
going to
in
be
my
able
job,
to finish this
and
video.
I've never encountered a switch that doesn't support the entire range, from 1 to 4094. Just be aware that some older switches might not support the extended range. Okay, so let's look at this diagram once again. So this PC in VLAN 10 wants to send traffic to this other PC in VLAN 10. The traffic goes to switch 2, which then forwards it to switch 1, with a tag indicating that the traffic belongs to VLAN 10. Switch 1 receives the frame, and because the destination is also in VLAN 10, it will forward the traffic to the destination. Remember, a standard layer 2 switch like this will only forward traffic in the same VLAN. It will not forward traffic between VLANs.
Okay, hold on. I'm not paying attention. I have to check to see when this meeting is supposed to be, because I'm pretty sure it's at 10 a.m. See you Monday at Okay. Hold on. Who'd this come from? Oh man, I did not prepare for this meeting like at all. Oh, and then Outlook email is so. Why is Outlook so bad? No, I need. Okay. I have to cut it short. I have a meeting, and I'm pretty sure it's in 20 minutes. So I gotta go get dressed and stuff and go. We will finish this. Dang, dude. Oh my God, man. If I wouldn't have been late, everything would have been better. Okay, but it's too late. I gotta just focus on what I gotta get done. So I will catch you guys later. We'll finish this up on Wednesday. We expect Wednesday to be a really long stream because we got a lot that we got to do, catch up on, and then move forward with. So I will catch you guys later. Yeah. Don't forget to subscribe to Jeremy, subscribe to me, work with what you got, build what you need, all that good stuff. And I will catch you on Wednesday.